Now, Cortex M4 has various power saving features. Now, the first point is not exactly a feature, but it's a fact that the die size and the process node contributes to power consumption. That is, if you have a 14 nanometer process node, it will definitely consume less power than a 32 nanometer process node, say, because the transistors are going to be smaller. If the transistors are smaller, then the power consumption is lesser. But of course, smaller die size or smaller process node has other complications, but let's not get into that. So that is one fact we have here. The high code density of Cortex-M processor allows software developers to use a microcontroller device with smaller program memory to implement their products to reduce power consumption. If we have a smaller, like we were talking in the previous slide, if we have a smaller amount of flash memory, if the flash is smaller, it will consume less power, of course, because to maintain the power through the flash memory, suppose higher it is, the greater power requirement it has. So definitely it is so I'm sorry about putting bullet points here. This is a continuation of the previous sentence, so sorry about that. So this is one sentence. The active current is mostly drawn by dynamic power needed by memories, peripherals, and the processor. So active current is when your processor is awake, it is running various peripherals, it is doing various jobs, it's doing some calculations and so on. So, and the clock is running for that particular processor, say at any clock frequency. For us, it's say 84 megahertz. So this is the active state, and the active state is the power consumption in the active state is roughly proportional to the clock speed. That is, the amount of power that is consumed at say 84 megahertz will be definitely higher than the power consumed at 42 megahertz. So when you slow down the clock, the power consumption goes down. So when you are doing your designs, you have to be careful about what clock speed you choose. And because if you choose a much higher clock speed than is necessary, then you might be wasting power. If your job can get done at a lower clock speed and it meets all the timing constraints, then it doesn't make sense to have a higher clock speed. And we learned that it is not even wise to have a higher amount of memory than you actually need, because that also adds to the power consumption. And it is measured in the microampere per megahertz. So the clock consumption is roughly proportional to the clock speed, and it's measured in microampere per megahertz. Now, the sleep mode current is generally composed of leakage current in the transistors and the current consumed by some of the analog circuits and the I/O pads, measured in microamps. Now, that is when the processor is in sleep mode. Okay, suppose the majority of currents at that in that state is consumed by leakage current in the transistors and the current consumed by some of the analog circuits and the I/O pads, and that is measured in microamps. And various run modes and sleep modes are available, like sleep and deep sleep for the Cortex-M controller. So in deep sleep mode, a greater portion of the SoC will be turned off. In sleep mode, maybe a few components or few parts of the processor would still be active, and deep sleep will consume even lesser power. Now, why not deep sleep all the time to save power? Again, sleep mode may have some advantages over deep sleep mode, which is why you might not want to put the processor in deep sleep mode all the time. Maybe the time taken to wake up from the deep sleep mode and go into probably an interrupt service routine might be higher. Okay, so deep sleep may not always be the solution. So you have to always think about basically a trade-off between power saving and efficiency and other factors. Ultra low power real-time clock. watchdog and brownout detector. So it can have a real-time, it has a real-time clock. Sorry, not that it can have, it has a real-time clock which is ultra low power. So when the processor is even in the sleep mode, this real-time clock can be active, and it has a watchdog and brownout detector also. Now, smart peripherals can operate while the processor remains in sleep mode. So suppose you are putting the processor in sleep mode to save power. Still, if you want to use certain peripherals, they can still be active while the processor is in sleep mode, thereby saving power. Now, flexible clock control features allow clock signals for inactive parts of the design to be turned off. Now, you can turn off the clock. So, say this is your core, processor core, and there are multiple peripherals which you are using, and each of them has a, this is not a resistor. I don't mean these are not resistors. These are clocks that you are feeding into those peripherals. Now, every time you feed in a clock to the peripheral and the peripheral is active, there is some power that is being spent here. So if you cut the clock to these peripherals, you save power here. So Cortex-M allows for saving power by cutting clocks to certain peripherals. Configurable clock speed to reduce power. For example, we said that you can have you can configure it to 84 megahertz. It has a PLL, so you can configure it to different clock frequencies as you wish. An interrupt-driven operation where the processor only wakes up during application processing and sleeps for the rest of the time. So there is a design paradigm where, say, you have this is the time axis, and the processor will only wake up, do its job, and then go to sleep. So, and this wake up is always triggered by an interrupt. So there's an external interrupt or any interrupt that comes in. It does its job. The moment it finishes its job, it again goes to the sleep mode. Then again some interrupt will come at some point. Again it will go into the sleep mode, and this interrupt may be periodic or non-periodic. So sometimes the interrupts may come in periodically, sometimes it may come in non-periodically. So what happens is the average power consumption, because it is going into sleep mode at the times where it is not needed to process anything, the average power that is consumed is lesser. So that is also another way of reducing power consumption in ARM Cortex processors. So when you design, you have to consider a lot of factors. There is a lot of trade-off that happens. So writing code on a microcontroller is not as simple and as straightforward. Coming to the processor architecture now. So before I even get into the processor architecture, I think this is the right time to talk about some data sheets and reference manuals that you have to download from the net. So going to that right now. So you can see there are some manuals and data sheets that I have. For example, this data sheet is the ARM Cortex data sheet for the processor that we are working on, that is STM32F411XC and STM32F411XC. So please pause this video and start downloading these data sheets. So this is the data sheet for these two processors. So you can download it from ST, or you can, if you search on Google, you can download this data sheet. These are all free data sheets, so you don't have to worry about paying for them. Another document that is a must to download is the programming manual, that is PM0214 programming manual for STM32 Cortex-M4. So this is the programming manual for the core, and it actually it caters to different microcontroller series. Okay, STM32F3, STM32F4 series. So this programming manual, so in the case of ST, I have seen that as you can see, there are multiple documents for which has to be downloaded and which has to be referred for you to understand one microcontroller. So this is another one, PM0214. So you need to download this. The third one, this is also a very important one, is the reference manual. Whatever I have written here is some annotations that I have put. This area is for the actual manual. Nothing of this sort will be written. I actually had mentioned the documents that need to be downloaded. For example, the documents that I'm showing you, so that for my reference. But this is another reference manual that you need to download. That is RM0383 reference manual for ST. That is STM32F411XC/E advanced ARM RISC-based 32-bit MCUs. Now, this talks mostly about the peripherals. So it talks about those aspects of this particular controller which is not common between others. For example, this talks about all the commonalities between the different microcontroller families of ST. So the programming manual is quite common for the core, and then this mostly deals with the peripherals and the memory system that this processor supports. For example, the flash management and the clock management is going to be different for this particular processor. Like we saw previously, that is, every vendor is going to, around the core, every vendor is going to design their own peripherals and memory systems and so on, right? So it's different for every vendor, like we saw. So this is how it is laid out. So ST lays it out this way. The commonalities, that is the core, is in this document, and peripherals and the memory system and the other aspects of the controller is in this particular document. Another document that you must download is the user manual for the discovery board itself. That is the discovery kit that we are going to work on. So we are going to work with the STM32F411BE discovery kit, and this is another document that you need to download, that is UM1842. So please download these documents, pause the video now, download the documents, and then continue with the course. Because if you don't download the documents now, you will find it very difficult to follow whatever we do henceforth. Because right through the course, we are going to refer to either of these documents. We will be looking into different features of the microcontroller and different aspects of the microcontroller, the registers, and how to program the registers. And at every step of the way, we are going to refer to these reference manuals and data sheets. Now, going back, this is the Cortex-M4 processor architecture, overall architecture. So we have a processor core which actually has the arithmetic logic unit and other parts, which is the actual Cortex-M4 core. It has the ISA instruction set architecture and everything. And then Cortex-M4 has a floating point unit sitting on top of that, which does the floating point calculations. Then it has the trace unit, that is, tracing is a feature of debug. So if you want to take traces of your application, this is the trace unit for that. Then you have the debug access port, which is used for debugging. Now we have the debug access port, which is used for debugging, which we shall see. That is, if we want to debug the program, we want to single step, set breakpoints, and we want to do all that. This debug access port, and this is internal to the Cortex-M4 controller. So from the processor core, you have a memory protection unit here, which we talked about, and then you have a flash patch, which is used for connecting to the flash. You have the data watch points, and then you have the SRAM and peripheral interface and the code interface, and this is the bus matrix. We'll have a look at the bus matrix shortly. So basically, it's the core, the FPU, and it is connected to various other peripherals. So peripheral in the sense, the serial wire viewer or memory protection unit, these are peripheral units to the processor core, but the actual peripherals, if you say, are the peripherals that we have, like your UART and GPIO and so on and so forth. So this is the peripheral interface, and the peripherals are actually outside here, outside this block. So this is in brief how the Cortex-M processor is laid out internally. And of course, the nested vector interrupt controller is also a very crucial and an important part of the Cortex-M4 architecture, which handles your interrupts. The bus matrix is again a very important feature of the Cortex-M4 architecture, and for this particularly, so we can see that this is the core, and you have some DMA units here, and there is a bus matrix, and we have the flash SRAM, AHB and APB buses outside, and there are some connectivity from here to here and so on and so forth. So at this point, suppose you have to look into the data sheet. Okay, so we will start seeing how to access the data sheet. So you will not know to begin with where to look for. So suppose you want to know more about the bus matrix. So what you need to do is you need to open those downloaded documents, and you have to search in there as to where the bus matrix is. Now, so this is where you will be having to reason. Since the bus matrix that we see here, the flash, the SRAM, all the peripherals and so on, they are unique to each of the hardware designer or the microcontroller vendors. So this is typical to the particular vendor. So obviously this will be found in the reference manual document. That is the document which has the data about that particular controller, not the common information of the Cortex-M4 core, but that is controller specific information. So here we see the diagram, and I've just copied this diagram into the slides. So system architecture, memory. So this is memory and bus architecture. So you have STM32F411XC or E. The main system consists of a 32-bit multi-layer AHB bus matrix. Okay. So it has a AHB bus, and there are 6 masters. So these are called bus masters here. Okay, so there are six masters. That is the Cortex-M4 with FPU core. Okay, I bus, D bus, and S bus. So these are the 3 buses. So we'll come to what these buses are doing. So these are the 3 buses. Buses are data paths basically. Then you have the DMA1 memory bus, DMA2 memory bus, and again DMA2 peripheral bus. And then you have 5 slaves. So these are the masters, and these are the slaves. That is the internal flash memory I code bus, internal flash memory decode bus, main internal SRAM, AHB1 peripherals including AHB to APB bridges and APB peripherals, and AHB2 peripherals. The bus matrix provides access from a master to slave, enabling concurrent accesses and efficient operation even when several high-speed peripherals work simultaneously. This architecture is shown in figure 1. Now, whatever you see here, these are connections. The round dots are the connections here. So as you can see, the I bus connects to the accelerator and the flash, and then on this line nothing else is connected. On the second line, which goes into the decode, that is the data side, you have the data bus connected, and then here you have the DMA connected and DMA MEM2. So these are the connections. Similarly, the I bus is connected to SRAM, the D bus is connected to SRAM, and all the DMAs are connected to the SRAM. So go by these connectors, dots actually. S bus is again connected to AHB peripheral 1, and so on and so forth. So this is just a set of connections that the bus matrix provides. Now all these connections cannot be active at the same time. So there is a scheme which is called bus arbitration, which is implemented here, whereby one bus at a time gets access to all of this, and the entire process is carried out in the hardware. Coming to the I bus now. The I-bus connects the instruction bus of the Cortex-M4 FPU to the bus matrix. The bus is used by the code to fetch instructions. The target of this bus is memory containing code, internal flash memory, or you can have code in the SRAM also. So this is the I-bus. So I-bus is again connected to the I code, as you can see. So D-bus is again connects the data bus of the Cortex-M4 with FPU. So don't be confused or don't get overwhelmed by whatever we are discussing. These are just data paths that we have, different data paths. Okay, and for example, so you have a D bus, you have a S bus, you have a DMA memory bus, you have a DMA peripheral bus. So different buses are here. I'm not reading this out. You can read them from the reference manual, and that is going to be an exercise for you as well. Read this, and chapter 2 is memory and bus architecture. You can have a read. So I'm touching upon, so these are buses. So the next one that is important is the bus matrix, which manages the access arbitration between masters. The arbitration uses a round robin algorithm. So bus arbitration again follows different algorithms. Like we discussed, you cannot have everything accessing everything at the same time. So it has to be, the buses have to be, these masters cannot all access these peripherals at the same time. So they have to take turns to do that. So that process where each master is going to be allowed the access to the bus is called arbitration. And the algorithm that is followed is round robin here. So we don't need to worry about that, but this is for your information. Now, these bridges are very important. That is AHP and APB bridges. So APB1 and APB2 provide full synchronous connection between AHP and the two APB buses, allowing flexible selection of the peripheral frequency. So we will have a look at the AHP and APB diagrams in the upcoming slide. So there are so many things that this particular section talks of. So we are not going to go into all that, but this is an interesting part of that chapter. Since I'm in the chapter, it's good to mention it, and that is the memory map and memory boundaries. So since we have a 4 GB flat address space for the Cortex-M4, so say you have a 4 GB flat address space here, so it's from 0 to 4 GB. All your flash and RAM, everything falls in this address. So you have code memory. So we will have a look at that as well, the memory map. So you have code memory, you have say data memory, and so on and so forth. You have flash, you have RAM, and all your peripheral control registers, whatever peripheral control is also a part of that same memory only. So everything is accessible using addresses on the same address space, and not all 4 GB is used. Parts of 4 GB are going to be used as per the as the processor vendor wishes, but the basic boundaries have to be respected. For example, for the peripherals, the addresses, the lower and the higher boundaries for the peripherals have to be at a particular memory location, and then the vendors can move that around. For example, for TI controllers, the flash starts from memory location 0, but in the case of STM, the flash starts from memory location 8000000. Okay, so that is where your coding memory has to be put, and the ST microcontroller starts accessing the flash memory from that location. So there will be differences like that between microcontrollers, which is okay, which is acceptable. Now these are different boundary addresses for, say, for the USB unit. All the USB control registers are within this address. DMA2 control is within this address. DMA1 flash interface, RCC. Okay, so RCC is extremely important. These are the main control registers for the microcontroller. Okay, so if you see the RCC, this is the RCC register map. You have to bookmark this page because you will be having to come back here over and over again, because I would say it is a bit weird. that all the register definitions or all the register information that you have in the reference manual here will only talk about offsets. So say we are on page 38 and say we go to say analog to digital converter, suppose. Okay, so say you are working on analog to digital converter, and then when you are looking at the registers for the analog to digital converter, just a moment. So let's try to go and look into the registers, ADC registers. Okay, so suppose you are looking at the register now, it only tells you about the offset. It does not tell you about what is the base for this ADC unit here, and that's a bit annoying, frankly speaking. Okay, and you don't the base address should have been mentioned here so that it is easier for you to know from where the ADC register is. Maybe you're using the CMSIS header files to access the ADC locations and all that stuff, but if you need to know, if you want to access it, write your own code, the place to find it is here. So you go to memory and bus architecture, and if you go down, this is from where you are going to find your address range, that is 04001 to 000. So if you go here, when it says offset 0, it means this address. So this is something that you have to keep in mind. Even though this was about bus, this segment was about bus arbitration and bus matrix, I thought that it is important for you to know this.